April 18, 2024. The interplanetary spacecraft. Juno, a mission launched by NASA to unravel the secrets of Jupiter, soared above the planet's mysterious northern polar region. What it captured in that precise moment would go on to stun scientists and ignite a new wave of curiosity. A swirling vortex of titanic proportions, a circle of giant cyclones rotating around a central storm, like dancers caught in a cosmic ritual. From afar, this may have seemed like another beautiful image of Jupiter. But Juno wasn't just taking pretty pictures. It was recording this event in 3 different spectra: visible light, infrared, and microwave. This multi-layered observation revealed something far more complex. Beneath Jupiter's iconic clouds lies a hyperactive atmospheric engine, pumping energy and motion in ways no planet in our solar system replicates. The microwave radiometer on board Juno enabled scientists to peer beneath the visible cloud layer, a breakthrough in understanding what powers these polar cyclones. Unlike storms on Earth that die off when separated from their moisture source, these Jovian cyclones seemed eternal, powered from below by something unseen and extraordinarily persistent. As data poured in, researchers from the Infinity Beyond team began noticing that each cyclone had its own core structure, different temperatures, and swirling speeds. And yet they formed a stable ring around the pole. Why didn't they merge or break apart? The answer may lie in Jupiter's internal heat, released in waves through its chaotic atmospheric layers. But this image was only the beginning. Juno's journey had already taken it over Jupiter's equator, its great red spot, and now its poles. With each pass, the spacecraft painted a deeper picture of a planet that doesn't just host storms, it is a storm. Unlike Earth, where weather is driven by sunlight, Jupiter's systems seem to be fueled by something far deeper: the remnants of its formation, still burning and moving after billions of years. In infrared light, the central cyclone glowed with intensity. Its temperature gradients showed heat rising from the depths, hinting that these were not just cloud-level phenomena, but massive, towering structures plunging deep into Jupiter's atmosphere. Think of hurricanes the size of continents, permanent, self-sustaining, spinning without end. And in microwave wavelengths, the reality got even stranger. The deeper Juno looked, the more it became apparent that Jupiter's polar regions weren't chaotic at all. In fact, they were remarkably organized, with precise structures and thermal boundaries that defied expectations. No turbulence, no merging storms. Just a perfect formation, a polar cyclone symphony. Why does Jupiter behave this way? What's the physics behind such perfect motion in such a chaotic system? Some theories point to the Coriolis effect, amplified by Jupiter's rapid rotation. Others suggest subsurface heat vents, vast upwellings of thermal energy that stabilize the cyclones by feeding them uniformly. And some more speculative voices even consider magnetic field interactions. But no one really knows yet. For the first time, thanks to the multispectrum imaging and precise instrument suite aboard Juno, we're now able to probe the invisible. We're not just looking at Jupiter, we're feeling its heartbeat. This heartbeat pulses through the atmosphere, pushing and pulling energy in ways that mimic, but also exceed, Earth's own processes. And it's not just the poles. The entire planet seems to be a fluid engine, spinning, convecting, radiating. It's a machine made of storms. The implications reach far beyond Jupiter itself. By studying these polar cyclones, scientists hope to unlock clues about exoplanets, especially gas giants that orbit other stars. If Jupiter's storms can remain stable for years, what might storms look like on even larger, hotter planets? Could their atmospheres sustain megastorms for centuries? Could their energy engines mimic what we're seeing, right here in our cosmic backyard? Back on Earth, the Juno team continues to study the images. The mission may have started in 2011, but its legacy is only beginning to unfold. And every time it swings by Jupiter, every data dump, every new pass over the poles brings with it more secrets. So the next time you look up at the night sky, remember, beyond those dots of light are worlds of unimaginable complexity. Planets that breathe storms, that twist and pulse with power. And among them, Jupiter stands as the undisputed king of weather. Juno saw not just a planet, but a cosmic phenomenon. And through it, we catch a glimpse of the boundless energy that fuels the universe. Stay with us here on Infinity Beyond as we dive deeper into the secrets of space, where every answer reveals 1,000 more questions. Winds, giant vortices, each unique in structure and behavior. The deeper Juno ventured, the more it revealed a planet not just chaotic, but harmonized by storms. To truly understand Jupiter, we must step back and view it as a planetary system, not just a single object. It's a world of layers, of cyclones, moons, magnetism, and ancient energy. One of the most captivating images from Juno shows Jupiter's south pole, taken from an altitude of about 32,000 miles. The scene is unlike anything in the solar system. Massive oval-shaped features dominate the frame, each one a polar cyclone, some over 600 miles wide. These storms spin in symmetry, maintaining balance in a way that defies simple meteorology. But Juno's mission wasn't limited to Jupiter itself. The probe also turned its instruments toward Jupiter's moons, particularly Io, the most volcanically active world known. Io isn't just a moon. It's a fiery, dynamic body that literally reshapes itself through continuous volcanic eruptions. Plumes of molten sulfur blast into space, visible even from hundreds of thousands of miles away. So what links Io to Jupiter's polar storms? That answer lies in the immense magnetic field of Jupiter, the strongest of any planet in our solar system. Io, orbiting within this field, becomes an electric generator, inducing currents as it moves, sparking auroras and possibly contributing to the dynamics of Jupiter's poles. What's even more fascinating is that these auroras, invisible to the naked eye, shine in ultraviolet and X-ray light, mapped for the first time thanks to Juno's instruments and Earth-based telescopes working in tandem. As Io spews particles into Jupiter's magnetosphere, they spiral toward the poles, creating massive energetic light shows deep in the atmosphere. Juno's data confirmed this interaction in stunning detail. Every time the spacecraft passed over the poles, it detected bursts of radiation, not just from internal heat or atmospheric convection, but from external interactions, especially from Io. In essence, the Moon and the planet are locked in a magnetic embrace, exchanging energy across millions of kilometers. And then came one of Juno's most astonishing discoveries. The polar cyclones themselves seem to shift subtly in response to changes in magnetospheric activity. Could this mean Io, and perhaps other moons, are influencing Jupiter's atmospheric structure in real time? The idea may sound speculative, but it's gaining ground. Scientists at Infinity Beyond note that the precise positioning of the cyclones and their long-term stability might not just be the product of atmospheric physics alone. Instead, it could be part of a larger electromagnetic system, a kind of planetary dance involving Jupiter's rotation, internal heat, and the gravitational and magnetic pulls of its moons. In that context, Io becomes more than a volcanic moon. It becomes a conductor, helping regulate energy through Jupiter's system. But Io's volcanoes also tell a story of their own. Juno flew close enough to detect thermal signatures from these eruptions, mapping hotspots across Io's surface. These aren't just small eruptions. Some volcanoes are hundreds of miles wide, blasting material so far into space that it becomes part of Jupiter's ring system. Yes, Jupiter has rings, faint and ghost-like, made partly from the dust and sulfur ejected by Io. All of this adds up to one mind-blowing realization. Jupiter isn't just a planet with moons. It's a planetary engine, and its moons are active gears in that engine. Every magnetic fluctuation, every burst of radiation, every volcanic tremor on Io, it all contributes to the story unfolding at Jupiter's poles. And Juno? It's the observer in the middle of it all, piecing together data to reveal the full architecture of this system. Even more intriguing, Juno discovered that the southern polar cyclones appear less stable than those in the north. Some are shifting in position. Some may merge. Why? Could it be the proximity to certain magnetic interactions? Could tidal forces from Ganymede or Europa also play a role? We don't have all the answers, but we do know this. No planet-moon system in our solar system behaves quite like this. Back on Earth, data scientists continue to analyze Juno's readings. Some are using AI models to simulate future changes in Jupiter's storm systems. Others are looking at similar signatures in exoplanets, suggesting that storms, magnetism, and volcanic moons might be universal traits in gas giants across the galaxy. This kind of science isn't just about looking outward. It's about understanding the patterns of motion, magnetism, and energy that connect celestial bodies. Jupiter and Io are the blueprint, a model of how seemingly separate objects can form a single living system. As Juno prepares for future flybys, scientists are preparing to use its final data to simulate Jupiter's inner layers, going deeper than ever before. And through this, they hope to answer a key question. What truly powers Jupiter, and how do its moons keep that engine running? Stay tuned to Infinity Beyond, where each new orbit brings us closer to the cosmic mechanics behind the largest planet in our solar system. Deep inside Jupiter lies a form of matter so rare and extreme that it doesn't exist naturally on Earth: metallic hydrogen. Unlike the familiar gaseous hydrogen that floats in Earth's atmosphere, metallic hydrogen behaves more like a liquid metal. It conducts electricity, generates magnetic fields, and forms the very core of Jupiter's mysterious interior. Thanks to the MEG instrument on board Juno, scientists were finally able to measure Jupiter's magnetic field with unprecedented precision. What they discovered was astonishing. The region where metallic hydrogen begins is much closer to the planet's surface than previously thought. This revelation shattered previous assumptions. For decades, scientists believed Jupiter's interior followed a simple structure: gaseous hydrogen above, followed by a gradual transition into liquid, and finally, metallic hydrogen deep down near the core. But Juno's findings told a different story: a dynamic, layered world with shifting boundaries and unexpected flows of heat and magnetism. Imagine hydrogen atoms under such extreme pressure that their electrons break free, allowing them to move like a metal. This is what fuels Jupiter's immense magnetic field, which is not only 20,000 times stronger than Earth's, but also wildly asymmetric. Instead of neat magnetic poles, Jupiter's field is lopsided. The southern hemisphere shows expected patterns, but in the north, the magnetic field bends and twists unpredictably. Juno's team at Infinity Beyond calls this region the Great Blue Spot, a mysterious magnetic anomaly still being studied. Why the asymmetry? Part of the answer lies in the behavior of metallic hydrogen. Its boundaries are not static. As heat and pressure fluctuate inside the planet, the region where metallic hydrogen exists shifts. This, in turn, affects how and where the magnetic field is generated. Beneath all of this, scientists long suspected a solid core, maybe a rocky or icy center left over from Jupiter's formation. But Juno delivered a surprise. There may be no solid core at all. Instead, Data suggests a fuzzy core, a central region where heavy elements are dispersed within metallic hydrogen, forming a slushy, swirling mix rather than a hard surface. It's as if Jupiter's core was dissolving into its own body, blending rock and gas into a planetary soup. This idea changes everything. It suggests that Jupiter formed in a more chaotic way than previously believed, perhaps through rapid accretion, capturing elements too quickly for them to settle. Or maybe intense collisions in the early solar system disrupted its inner structure. Either way, Jupiter's heart is not solid. It is in motion, reshaping itself over time. And this internal chaos may be connected to what we see on the surface. Juno observed zonal winds, powerful jet streams that wrap around the planet. Unlike Earth's jet streams, which are confined to the atmosphere, Jupiter's penetrate deep below the cloud tops. In fact, some of these winds reach thousands of kilometers into the planet, driven by internal heat and rotation, not sunlight. These winds twist and stretch the planet's magnetic field lines, creating auroras, storms, and possibly even influencing its rings. The entire planet is in motion, from core to cloud. One of Juno's key revelations is how this motion affects Jupiter's gravitational field. Using a technique called gravity mapping, the spacecraft detected small changes in its orbit caused by Jupiter's mass distribution. These changes revealed not only the extent of the zonal winds, but also asymmetries in how material is distributed inside the planet. It's like using a tiny vibration to reveal what's inside a solid object, and what it showed is that Jupiter is not uniform. It's layered, turbulent, and evolving. And that brings us to a deeper question. Is this behavior unique to Jupiter? Possibly not. Many exoplanets, giant gas worlds orbiting other stars, may also have fuzzy cores, zonal winds, and magnetic fields generated by exotic matter like metallic hydrogen. Jupiter may be a prototype, a cosmic test case for understanding how massive planets behave across the galaxy. Back on Earth, researchers at Infinity Beyond are developing simulations based on Juno's data. These simulations don't just model Jupiter's present, they attempt to rewind time, showing how such a world formed, changed, and might continue to evolve. They've even speculated about what would happen if Jupiter had been just a little more massive. It might have triggered nuclear fusion, becoming a star. But it didn't. It stopped just short, remaining a planet, but one so massive it still glows in the infrared, leaking heat from its formation. That glow is the final clue. Jupiter radiates more energy than it receives from the Sun, a clear sign that its engine is still running. Deep inside, metallic hydrogen flows and convex, driving a magnetic field, shaping weather, and maintaining the zonal winds. It is a planet that, in many ways, still remembers its birth. And thanks to Juno, we're now finally reading that memory, layer by layer. Stay tuned with Infinity Beyond as we continue decoding the secrets of Jupiter's hidden heart, a world of liquid metals, fuzzy cores, and magnetic mysteries. Jupiter is not just a planet, it's a gravitational king, and its court of moons tells a story as captivating as the giant itself. While its turbulent atmosphere rotates in bands and zones, with winds reaching 328 feet per second, some of its most profound mysteries lie not in the sky but beneath the icy shells of its moons. Two names stand out: Europa and Ganymede. Europa, though just slightly smaller than Earth's moon, may hold one of the greatest scientific treasures in our solar system, a subsurface ocean. Beneath its cold, cracked ice sheet lies a vast body of liquid water, possibly twice the volume of all Earth's oceans combined. Juno, though primarily focused on Jupiter, made critical observations of Europa during its flybys. Using its instruments, it mapped temperature anomalies, tracked tidal flexing, and confirmed that heat from within is keeping Europa's ocean liquid, despite being so far from the Sun. This internal heating is driven by gravitational interactions with Jupiter, much like Io, but without the volcanic chaos. Instead, Europa's interior flexes rhythmically, creating friction and generating enough warmth to sustain liquid water under the ice. But it gets even better. In some regions, cracks in the icy surface may allow plumes of this underground ocean to burst into space. These plumes could carry with them organic molecules, possibly even signs of life. Instruments on Juno and Earth-based telescopes have detected hints of water vapor, the cosmic equivalent of a message in a bottle. Europa is a prime candidate for life, not because it looks like Earth, but because it doesn't. Its alien environment, driven by tidal forces and protected by an icy shell, offers a unique laboratory for testing how life might arise in extreme conditions. And if life exists there, it would change everything. Ganymede, on the other hand, is in a class of its own. As the largest moon in the solar system, Ganymede is bigger than Mercury. It's the only moon known to generate its own magnetic field, which interacts with Jupiter's in spectacular fashion. Juno's flybys revealed layers of structure beneath Ganymede's crust, including what appears to be a saltwater ocean sandwiched between layers of ice and rock. Imagine this, not just one ocean, but multiple liquid layers, stacked and separated by different types of ice. This complex stratification suggests a world with active geological and thermal processes, protected from radiation by its own field, something no other moon can claim. The implications for habitability are profound. A magnetic field means protection from solar and Jovian radiation. Liquid water means chemical reactions. And heat from within suggests the potential for energy, one of the key ingredients for life. Together, Europa and Ganymede represent a new frontier in astrobiology. Not worlds to be colonized, but worlds to be listened to, studied, and respected. They may already harbor life in forms we haven't yet imagined, microscopic, alien, and hidden beneath ice thicker than Mount Everest is tall. But why stop there? Juno's mission, and future missions like Europa Clipper and JUICE, Jupiter Icy Moons Explorer, aim to go even further. By analyzing the chemistry of these moons, their electromagnetic environments, and possible cryovolcanism, scientists at Infinity Beyond hope to answer a question that has lingered for centuries. Are we alone, even in our own solar system? If life exists beneath Europa or Ganymede, it would prove that life doesn't need sunlight, Earth-like temperatures, or even dry land. It would suggest that life is not a rare cosmic accident, but a common consequence of water, energy, and time. The story also connects back to Jupiter itself. The planet's immense gravitational grip shapes the orbits of its moons, stirs their intrigue, and possibly even delivers the energy that keeps their oceans alive. Jupiter is not just their host, it's their life engine. Even the auroras of Jupiter bear the fingerprints of these moons. When Ganymede crosses through Jupiter's magnetosphere, it triggers its own auroral footprint, a shimmering signal of its magnetic presence. Europa does the same, albeit subtly, indicating that each moon is plugged into Jupiter's electromagnetic heart. And in this grand cosmic circuit, every interaction matters. Each gravitational tug, each magnetic pulse, each ripple through the ice, it's all part of a complex, interconnected system that makes Jupiter's moons some of the most compelling places in the solar system. Juno's continued study of these moons, alongside the upcoming orbiters, is set to usher in a new era of ocean world science. Europa, Ganymede, and perhaps even Callisto may yet teach us more about habitability than Mars ever could. So as we look beyond Jupiter's clouds and into the icy darkness beyond, we're not just exploring moons. We're searching for echoes of life, for answers to ancient questions, and perhaps for reflections of ourselves. Jupiter isn't just the largest planet in our solar system. It might also be the most important reason Earth exists as it does. With its colossal mass and gravitational pull, Jupiter acts like a cosmic shield, protecting our planet from some of the universe's most dangerous threats: asteroids and comets. At over 300 times the mass of Earth, Jupiter's gravitational influence stretches far beyond its orbit. Anything that ventures near, be it an icy comet from the outer solar system or a rogue asteroid from the asteroid belt, can be deflected, captured, or redirected by Jupiter's immense gravity. In fact, Jupiter has likely absorbed or deflected countless impacts that might have otherwise struck Earth. It's been called our Big Brother, guarding the inner planets from celestial danger. Without Jupiter's presence, life on Earth might have never had the chance to evolve. But Jupiter's role in shaping the solar system goes deeper than defense. Billions of years ago, during the chaotic formation of the solar system, Jupiter's movement through the young protoplanetary disk reshaped orbits, scattered debris, and possibly even flung objects toward the early Earth, delivering the building blocks of life. Some theories suggest Jupiter's migrations, first inward, then outward again, helped stabilize the inner solar system, ensuring that rocky planets like Earth could form and survive. Without this migration, our solar neighborhood might be filled with super-Earths or gas dwarfs, not habitable worlds. But Jupiter doesn't just push things away. Sometimes it captures them. Jupiter has a host of Trojan asteroids, ancient rocks that have orbited with the planet for billions of years. These objects may be remnants of the early solar system, frozen in time, carrying secrets from the dawn of planetary formation. And when things do collide with Jupiter, the planet wears the scars proudly. In 1994, astronomers witnessed one of the most spectacular events ever recorded. Comet Shoemaker-Levy 9 slammed into Jupiter's atmosphere. The impact left visible dark spots the size of Earth, clear evidence of Jupiter's sacrificial role in our planetary safety. Juno and telescopes on Earth continue to observe new impacts: flashes of light in Jupiter's clouds, sudden storms triggered by kinetic energy. Each impact reminds us of the dangers that exist beyond Earth and the giant that stands between us and those dangers. But Jupiter's role isn't just external. Its own atmosphere is a layered masterpiece, bands of gas swirling in opposite directions, creating storms that last centuries. Thanks to advancements like Lucky imaging, scientists have captured the most detailed photographs of Jupiter ever taken from Earth, revealing textures, colors, and motions once hidden in blur. Lucky imaging works by capturing thousands of frames per second and combining only the clearest moments, giving us visuals sharp enough to distinguish individual storm structures, lightning flashes, and subtle color shifts across the bands. These images, combined with Juno's data, have revealed Jupiter's multi-layered atmosphere, composed of ammonia clouds, water vapor, and deeper, denser hydrogen layers. By studying these layers, scientists at Infinity Beyond are learning not only how Jupiter functions, but also how giant exoplanets might look in other star systems. Even more impressive is how deep the atmosphere rotates. The planet's iconic bands aren't just surface features. They extend thousands of kilometers downward, driven by internal heat, rapid rotation, and the planet's fluid dynamics. This discovery bridges the worlds of planetary science and physics, offering insights into fluid motion under extreme pressure, something that applies not only to planets, but even to stars and neutron stars. And Jupiter's influence doesn't end with Earth. Its gravitational effects shape the asteroid belt, create resonances that govern orbital patterns, and even help regulate the orbits of Saturn, Uranus, and Neptune. In a way, Jupiter is the solar system's anchor, keeping the entire planetary family in relative order. Without it, chaos might reign. But Jupiter's power is not absolute. Sometimes its gravitational pull can redirect objects almost inward, pushing comets or asteroids into dangerous paths. It's a cosmic double-edged sword, both protector and occasionally inadvertent threat. This duality is part of what makes Jupiter so fascinating. It's a planet of contradictions, a stormy giant that brings calm, a chaotic atmosphere that hides elegant patterns, a distant world that plays a critical role in Earth's story. And as Juno continues its mission, orbit after orbit, the secrets of Jupiter become clearer. It's not just a gas ball. It's a dynamic system of storms, fields, and gravity wells, a living machine sculpted by time and physics. Every pass of the Juno spacecraft refines our models, validates our theories, and challenges our assumptions. What we learn from Jupiter doesn't stay at Jupiter. It echoes across our understanding of planetary systems, asteroid dynamics, and the conditions that make planets habitable. So next time you look up at the night sky and spot that bright wandering star, remember, that's not just another point of light. That's Jupiter, the cosmic guardian, the storm maker, and the gravitational force that shaped our home more than we realize. It's the most iconic feature on the largest planet in the solar system, the Great Red Spot, a storm larger than Earth that has raged on Jupiter for over 300 years. But recent data tells a surprising story. This ancient tempest is shrinking, and scientists are racing to understand why. The Great Red Spot is essentially a superstorm, a high-pressure system unlike any on Earth. It rotates counterclockwise in Jupiter's southern hemisphere, with winds peaking at over 430 km/h, 267 mph. It's big, it's violent, and it's mysterious. And yet, it's fading. Why? According to recent observations from Earth-based telescopes and NASA's Juno spacecraft, something in Jupiter's atmosphere is slowly tearing the storm apart. In May 2017, astronomers using the Gemini North telescope detected a small, hook-shaped cloud breaking off from the storm's western edge, followed by what looked like a wave peeling away on the eastern side. It wasn't just a glitch, it was a pattern. Juno's high-resolution cameras captured red flakes, pieces of the storm's outer layers being torn away and flung into the atmosphere. These events, observed more than once, suggest that Jupiter's atmosphere is destabilizing the storm from the outside. That raises a critical question. Could the Great Red Spot actually disappear within our lifetimes? Some models suggest it might shrink to the point where it's no longer visible, or at least no longer recognizable as the massive oval we've seen for centuries. And while that might seem sad to space lovers, scientists are thrilled, because this gives us a once-in-a-lifetime opportunity to witness planetary-scale weather evolution in real time. But what exactly is causing this? The leading theory involves zonal winds, the same bands that dominate Jupiter's atmosphere. These powerful currents, moving in opposite directions across latitudes, may be siphoning energy away from the Great Red Spot. As the winds change speed and position, they interact with the edges of the storm, chipping away at it like waves eroding a coastline. Another possibility involves heat gradients. Jupiter emits more heat than it receives from the Sun, and this internal energy drives much of its atmospheric motion. Changes in heat flow from the interior could be altering the stability of long-lived storms like the Red Spot. Whatever the cause, the decline is measurable. In the late 1800s, the storm measured over 40,000 kilometers, 25,000 miles wide. Today, it's closer to 16,000 kilometers, or 10,000 miles. Still massive, but less than half its original size. Its color has also changed, shifting from a deep brick red to a more muted orange. This might be due to changes in chemical composition or exposure to different radiation levels. Still, the red spot remains powerful, continuing to rotate and trap atmospheric material within its walls. It's shrinking, but not yet dying. In fact, some researchers believe it may stabilize into a smaller, long-lived cyclone, much like the one seen at Jupiter's poles. The Juno spacecraft has given us unprecedented insight into the depth of the red spot as well. It's not just a surface storm, it extends hundreds of kilometers deep into Jupiter's atmosphere. Juno's microwave and gravity instruments confirmed that the storm penetrates much farther than previously thought, possibly connecting to deeper layers where heat and motion originate. That means this isn't just a cloud pattern. It's a vertical engine, tapping into Jupiter's internal energy, and still very much active, though evolving. The Great Red Spot also plays a role in heat distribution. By stirring the upper layers of the atmosphere, it helps transfer heat from the planet's core outward. As it shrinks, the effects on Jupiter's weather systems could be significant, changing wind patterns, storm frequencies, and cloud formations across the entire southern hemisphere. Back at Infinity Beyond, scientists are using Juno data to build simulations of Jupiter's future. Some of them suggest that if the red spot does vanish, it may reform elsewhere or give rise to multiple smaller storms that follow similar paths. After all, Jupiter is a stormy world. It has the fuel to generate new monsters at any time. So, should we worry? Not really. The disappearance of the red spot is not a threat to Earth or the solar system, but it is a rare cosmic event, one that gives us a glimpse into the lifespan of weather systems on gas giants, systems that make Earth's hurricanes look like gentle breezes. The bigger takeaway is this: even the mightiest features in our solar system are not eternal. They are born, they evolve, and they fade. And thanks to modern technology, we get to witness that cycle from afar. The Great Red Spot has been a symbol of Jupiter's power for centuries. Its legacy will continue, whether it persists for another 100 years or fades within a decade. But for now, it still spins, a scarlet eye gazing out from a world of gas, storms, and gravity.